Welcome everybody to this edition of the PRIMA PCast series. So we're a little bit off cadence this week and working at a special time. So glad those of you who are able to join us in person are able to join us in person in real time. And of course, the talk will be recorded and we will post it so that if you weren't able to make it in real time, you will still have access to the great talk that we're going to hear today. But before we get to that, I had just a few housekeeping announcements sort of things that I wanted to take us through. First is the big news that the GeoBook Volume 2 is coming together in a big and exciting way. We had more than 120 submissions. This was over 430 unique authors contributing to this book from 34 different countries. So our GeoBook editors are very hard at work on double checking the time calculations, doing editing, feedback with the authors, and we are anticipating that we'll be able to publish the full new volume sometimes next month. So a huge thank you to everybody who took the time to write up a case. I think it is really showcasing the tremendous community appetite for PRIMA, and we are very excited and grateful for all of these excellent contributions. Another news on the PRIMA front is that we have a PRIMA special issue of JWST, and that is in progress now, so you can find it on the JWST website here. And we're also going to have a major PRIMA archive day that will be on September 3rd, where a large fraction of these papers that constitute the JWST special issue will be posted to archive. So it should make quite a splash on the September 3rd archive posting with many, many PRIMA papers. So please look forward to that. And thank you everybody who will be submitting their JWST contribution to the archive at that time. Okay, so that's all the announcements I have, so we can turn to our program for today. So it's our delight to have Yao-Lun Yang from RIKEN joining us today. Thank you, Yao-Lun, and who's going to be talking to us about molecular and atomic outflows at the early stage of star formation. Just quickly, the two upcoming talks I would like to advertise. On September 8th, note that that is a special date. We'll have Klaus Pentapeten from JPL Caltech. And then on September 22nd, we will have Vivian Yu from IPAC. So lots of excellent stuff coming up for PRIMA PCast talks over the next month. And so now I'm going to stop sharing my screen and turn it over to Yao-Lun. If I can find the stop sharing button. Okay, there it is. Okay. So we're delighted to have you, Yao-Lun. So if you want to share your screen and take it away, we're very much looking forward to your talk.
Okay. Is this working?
That looks great.
Okay, cool. For some reason, I couldn't see you videoly. So if there's anything anyone want to say anything, just shout and let me know. Great. First of all, I want to thank the invitation to give a talk today, and thanks for arranging the time so that it's not too crazy from a Japanese side. Yeah, so today I'm going to talk about some molecular outflow and atomic outflow, and actually I will talk about a little bit about ionized outflow in early stages star formation. And today I'm mostly going to focus on sort of like a protostar stage and to see how we can use various different observation like wavelength and instruments to characterize the outflow and why we want to characterize an outflow. And I think, and also hopefully in the end, you will see how PRIMA can be sort of like game changers in probing the particular atomic and ionized part of outflow in protostars. So a very simple kind of overview or kind of introduction of how the outflow is important for star formation in general is we can see from this very, very simple kind of cartoon figures for the kind of evolutionary of star formation of starting from a core, and this core collapse under gravities basically, and then there will be some angular momentum in the the system need to get it out, need to remove from the system to allow further inflow, and so that a disk can form. We do know planetary systems do form in the end. So this angular momentum removal process typically go through in the form of outflow. So this outflow represent that process, and also the long-term outflow can be regulated by the magnetic field configuration in the center around the disk, and also along the outflow propagation. So the outflow could be accumulated, could be regulated by the field structures in the envelope. Yeah, so a lot of these outflow study that we try to do, or why we look into outflow, is first of all, it's very easy to see, and then once we see outflow, it could have indication of, first of all, it means that there's a disk at the center, and observing a disk is much more difficult than observing an outflow. Observing a disk will require to have exceptional angular resolution, and also require to have ideal tracers, because disk is very dense. So sometimes you're just limited by optical depth. So outflow is kind of another probe that we can use to probe disk and accretion ongoing in a disk. So observing outflow and characterizing outflow dynamics, its outflowing rates, its structure, whether it's collimated, its variabilities along the outflow has indirectly, but also the direct link to the disk underneath. So, like I said, outflow is very easy to observe. So we have already seen that for various infrared and some millimeter observation. So here shows like a sort of like a one of a famous example of a cluster star forming region, NGC 1333. So you can see on the left figure, I think this is a Spitzer image showing a lot of these again green stuff look like a little wimpy, and sometimes if you look closely, look like outflowy kind of structure. Those are likely tracing molecular hydrogen shock in outflow. So they come in different shape and form, and on the right hand side, it's I think it's a carbon observation of outflow in the same region, and now we can clearly see the blue and redshift side of outflow, suggesting most of them are bipolar, but you can still see they all come with different morphology. Some of them a little bit wider, some of them a little bit more collimated, and they're more well-structured outflow versus less structured outflow. So they all represent how the outflow is propagating and how it's interacting with the surrounding system. And the outflow itself also have various structure as well. Sometimes there's a kind of a wide spectrum of the terminology people use. Some people say jet, some people say outflow, there's winds. But normally, I think when we say jet, it means a very collimated outflow or collimated kind of ejection away from a protostar. And outflow could be a wide angle one, also could be a overarching term for everything that is outflowing from the protostars. So this is showing a numerical simulation by Machida et al. In 2015, where they showed that in their simulation is naturally creating a jet embedding with an outflow. So in their simulation, they basically have two outflow components. There's one lower velocity outflow, which is wide angle, and there's a jet in the center, which is higher velocity. You can have velocity up to 70 or even 100 kilometers per second. So that really tell you that there's multiple kind of have distinct physical properties components inside the outflow, that it is more complicated than just some gas moving out and creating an outflowing structure. So observationally, we also see that. So on the left hand side, it's a protostar called HH212. So here shows various different tracers here, but the most I want to draw your eye to the blue one, which is the H2 molecular hydrogen, and there's a green one, and green and blue there are SiO and CO, and you can see here all of these things trace a very narrow kind of really collimated outflow or like jet-like structure. And so this is very distinct to see that this jet doesn't need to be normally within jet is very high energy or highly excited material tend to be in ionized gas. I think in infrared observation is often easily pick up with iron 2 emission, but we can also see in molecular jet. So here show a very wonderful example, and we can also see there's some variation along the jet direction, suggesting that it could be a variation in outflow rate. Maybe the gas is ejecting in episodes, which could indicate that the accretion underneath is also occurring in episodically in corresponding to the outflow ejection. And on the right hand side is another protostar called B335, and in this case we're seeing this wide angle outflow. This is tracing by CO, is observed by ALMA, so a lot of extended structure is being resolved out, but we now see this really kind of almost symmetric wide angle outflow here with some material or some sort of like collimated or maybe a little bit clumpy structure inside. So, and it demonstrates that it could be, even for both of these sources are considered to be a pretty young embedded protostar, but this seems to have very different outflow signature and seems to have very different structure in the outflow that is picked up by different they can represent even in a same tracer. So like, in a CO on the left it shows a collimated jet, on the right shows a wide angle outflow. And so ALMA has been a very excellent machine for this outflow characterization. It has superb resolution. It can observe molecular lines, and sometimes very rarely atomic line like C1 in very high resolution and high velocity resolution, so that allow us to map out those outflow and also measure their kinematics properties. So I'm showing a gallery from Xie and O in 2023, where they're conducting a really nice survey in the protostar in Orion, showing, looking to outflow structure, looking to the mass outflow rate and as a function of distance. So I'm not going to their detail, but I think this is sort of the latest in terms of outflow studies. And here I wanted to again emphasize that these outflow come in different shape and forms. So we go from really well-organized outflow sort of in the top row or maybe middle rows to the bottom rows, kind of like all shows irregular shapes, and then sometimes it could be due to inclination. Maybe we're viewing those system sort of like almost face on, but sometimes really just the nature of outflow, nature of source look at this, and sometimes we only see one side of one lobe of outflow, and there's some we still don't quite sure why in some sources we only see one-sided outflow, and this could be also related to how the outflow is reacting with interacting with the surrounding material. And another way we can pick up sort of different structure or the structure within the outflow is to use different tracers. So here is a example for that. So we earlier this year we published a papers using our ALMA data, using by looking into the C2H emission compared to SO emission to see that whether these two molecules give us different morphologies in outflow. So on the left, it's a map of these two tracers compared to the continuum. So continuum is showing in grayscale, and the C2H is showing in blue. Sorry, in green, in red, and the SO is showing in orange. And then this is obviously a little bit fuzzy to look at, so we develop a methods. Basically, we're going to measure the radial distance of these emission in different sources, and then kind of plotting in the same scale. And for those two tracers, that's resulting in the figure on the right. So we can clearly see that not only does C2H locate in a larger distance compared to SO, we also see that the SO, basically the distance where SO emission appear, a C2H emission seems to avoid that. And so it's not just like one event is more extended, the other one is more compact. It's almost seems like there's a mutually exclusive presence of these two molecules. Like, and in this paper said Jack Anderson, they discuss even more about why this could be what kind of scenario could lead to this this situation. And one thing we conclude on is that the C2H will likely appear in a carbon-rich gas and in a center of outflow when you have more molecules released from a dust grain, you start to have an oxygen-rich gas, and therefore it's easier to form SO or have SO survive there. So this shows that different tracers will pick up different part of outflow, and that could represent both a physical change in outflow, could also represent a chemical structure within the outflow. And obviously, JWST has been excellent machine to mapping those star forming regions, and as we already see, those previous figures with Spitzer are showing a lot of outflow, and this kind of expect that JWST is going to pick up a lot more outflow as well. And it has been. So in this paper in Green 2024, they're looking to a region called Serpent's Man, and basically characterizing all of this outflow within this region with near cam images. And so on the left is the outflow they identified on a large scale image. On the right is in the individual snippet or like cutout shot of this individual outflow. So again, we already seeing like outflow comments to different shape of form again here. Some of them look pretty nice wide angle, kind of triangular shape. Some of them more like a parabolic. Some of them only see kind of arc-like structures propagating to one direction or both direction. And one thing they found in this interesting in this study is that they found the outflow direction seems to be aligned with large-scale magnetic fields, even in a cluster region. So it shows that perhaps the angular momentum or the rotation of a source in a cluster star forming cloud that could, and those rotation have a preferred direction under the large scale B field, not just like a small scale that outflow is regulating by the local magnetic fields. And JWST can also do an excellent job in spectral mapping for those outflows. So this is demonstrated by a study last year on HH211. So this is a very beautiful outflow. There's this like color image which I didn't really able to find a place to show, but I'm sure some of you must have looked into that figure already. But here I'm showing like a black and white version of that from their paper, and so they have this image of this outflow in the background, but then they have this spectral map, this blue and red region with MIRI and NearCam, MIRI and NearSpect, try to capture those knots, obtaining full spectrum in I think it's about 228 micron or so. And one thing they can do by having those coverage is that they will observe many molecular hydrogen lines and probing, then can use those line series to constrain the molecular hydrogen gas property within the outflow. So on the right, it's one of a result that they came out basically showing the distribution of the warm H2 gas and versus the hot H2 gas. You can see that the hot H2 gas is more compact and a lot more clumpy than a warm H2 gas. So with H2 line, we can already see there's some temperature structures within the outflow, and even within this jet structure, kind of very smaller, closer to the protostar on the top right corner of each figures. Okay, so then I want to show another example that we also found a very interesting structure in an outflow in a protostar system called RS15398 3359. So it's a young protostar, it's class 0 with very prominent outflow, like the one shown here. This is the ALMA CO observation. You know, one of the kind of regular looking outflows you will see. And but then in ALMA, people actually found some interesting feature of this source where there seems to be other kind of outflow like structures further out in a few thousand AU scale. And their kind of running interpretation is that there could be multiple outflow in the past, had very different direction or something. So that will be interesting too. But one thing I want to kind of focus on, and sort of like one thing we accidentally stumble on, is that we obtain this like near this mirror image kind of by chance as part of our JWST observation. This is actually coming from a background pointing that we randomly choose, and this is from a simultaneous image that we did with mirroring at this chosen background position. So and it happened to land on the source. So and we are really excited to see we actually capture some part of outflow. And that's why the orientation figure the coverage is not ideal. Otherwise we could have moved like just 3 arcsecond to cover the source. But in any case, we see these like beautiful shell-like structures within the outflow. This is a composite image from 5 micron to 10 micron. And then we also see this seems to be a terminal position where it look like a blue dot on the shell 4. And we think this could be due to maybe a terminal shock when it's like a lot more bluer. And it's just a lot of structure. If we zoom into this figure, we can see a lot of like structure within this between the shell actually. So we're really interested to see what's going on with this outflow, like why they are what this shell structure actually represents, and how it's like corroborating with our other observation signature of this particular system. So in a smaller scale, like I mentioned, we do this is our main science program. In this observation is to do spectroscopy observation and tour small sample of protostar. This is from a CRENO program that I have been leading. So this just showing a gallery of lines we can get. This is mostly this is ionized line, so we have 4 iron 2 line here and neon 2 and nickel 2. We can all see there's a tracing a wonderful jet-like structure here, and they even look like some knots. You can see there seems to be a knot in about 2-ish arcsecond away in the south and the southwest, and it's also quite interesting that because a jet or a jet in any kind of tracers is not being detected with ALMA. So it means that there's no molecular jet, but then we do see very, very clearly ionized jet signatures in this protostar, and which has never been seen before. With a series, our observation will also include a series H2 line. Now it's not as much as the previous study I mentioned on HH211, but we still have 8 lines, so we can do some fitting in some characterization modeling of these H2 emission to figure out what are the H2 properties in the outflow. So what we did is that we can look into so we basically did a few things here, but one thing I want to demonstrate here is that we do see the H2 emission morphology changing as a function of different transitions. So if we go from S1, which is like the lowest excitation H2 line, we can robustly detect with JWST. Note that the S0 line 28 micron is technically covered by JWST, but it's very difficult to observe because sensitivity drops quite a bit, and PRIMA should be able to do that. So although I'm probably not going to focus on that, but I think that's a very, very important part that we should keep in mind, because that traces the coldest part of H2 gas that JWST cannot robustly measure. Anyway, so we do see S1 line and maybe lower excitation line here tracing a wide angle outflow, and as we move to higher excitation line, we start picking on this like compact structures, maybe some knots, very similar to perhaps very similar to the knots we see in iron 2, but they seem to have a different morphology here. But it does suggest that there's some internal outflow structure that that is we can see that from having multiple H2 lines here. And now we're very interesting to see whether this shell-like structure we see in the mirror image, whether they have any correspondence in other traces as well. And so we compare with some ALMA data. We do see that there seems to have some correspondence with H2CO for monohyde. So that's shown in the bottom panel. Compared to with CO, it seems to be maybe not, but this is really most obvious seen in H2CO, and by just comparing with ALMA, it's still very difficult to see what could be a potential reason for creating this kind of shell-like structure. But we also look into different parts of one way to kind of interpret this shell-like structure is there could be multiple episodes, you know, like you just have different episodes of ejection. And actually people do analyze this CO emission and try to propose those kind of things, like there could be some outflow precession or multiple outflow ejection happening in the source. And from our observation, we also see that there's like, just by looking at the iron 2, which is traced by this red dashed line, and compared to our mirror imaging of this multiple shell-like structure, we do see some about few degrees difference in position angle of outflow. So they do suggest there's some precession as well. In the paper, we discuss more about what kind of time scale you trace or something, but it is kind of generally consistent with the precession scenario proposed in our study, although it doesn't really provide a smoking gun evidence suggesting this shell-like structure is indeed tracing multiple ejection. It's interestingly that we also, through one of my collaborators, we look into kind of a very different approach that for the outflow study to try to interpret this structure. And one thing we pick up is we saw this kind of studies on under-expanding jet in kind of aerodynamics or fluid dynamic field. This is mostly in a study of like the jet stream from the plane or something, and we do see that in a certain input or initial condition of a ejecting jet, with basically the condition here defined as the pressure of injection and the pressure of surrounding, and you could have a so-called under-expanding jet and creating a structure called mock disk, which is one shown on the right. And also showing a kind of like the second row and a time average column, and kind of toward the bottom, you can start to see just like you can create this kind of like barrel-like cavities that can steadily form in this kind of jet. So we think this is kind of morphologically very similar to what we see in our protostar, in our mirror image. So we ran some simulation, and we actually found that with the right kind of simulation, we do create a very similar structure, although it only the downside is that it's mostly just representing the first kind of shell structure, but if you want to go further out, it starts to become a lot more difficult. But the goal here is to do a kind of proof of concept to see whether this could be potentially a feasible method, and if so, this can have very useful indication about using the outflow structure, because then we can use this structure of outflow to predict or to infer the pressure ratio, and the pressure ratio is directly related to the launching mechanism of the outflow. So this potentially provide a connection to the morphology of substructure of outflow directly to the accretion launching mechanism down toward the protostar, where it's very difficult to observe. And so to conclude this part, I want to highlight that there's a lot more outflows being observed. In fact, there's a dedicated have a large program with using JWST. We're mapping OMC 2 and 3 with both imaging and IFU spectroscopy. So this showed, I think all of our data are taken, but this showed the near-cam image, a very beautiful near-cam image we got. And if I can zoom in, like you can see there's a lot more outflow structures and different tracer shapes. So there'll be a lot more new things we're going to learn here. And obviously this is large program, so this is for community as well. So let me know if you have any interest, but this is something we're currently actively working on, try to kind of provide a first look of what JWST can do and what we can learn more on outflow and accretion science using kind of state-of-the-art inference observation. So I hinted many times, like kind of like along the way, that the outflow is not a single entity, have a structure inside, and I think this figure summarized those structure very well. It's basically a nested structure where we have an outflow, like wide angle wing mostly traced by molecular gas. And then as you move toward the center part, toward the jet, you start to have atomic gas, you start to have ionized gas in the center, and your temperatures start increased as we go to the center of a central part of the jet. And along the jet, it could be different shock or something that result in those like bullets or shell-like structure, arc-like structure along the way, along the outflow propagating region. So this is sort of like a picture where we're coming together here. But one thing that is missing, I think, in most of these tracers is atomic outflow. So you can see that I show iron 2, I show neon 2, I show H2 molecular hydrogen, I show CO, but it's very difficult or very few tracers that can trace these atomic components of outflow. And we know that from molecular gas to ionized, it probably has to go through atomic phase. So we want to know what's going on with the atomic outflow. So this has been studied quite a lot with Herschel. So I want to kind of show you basically what Herschel can do and has been doing in the outflow study, and slowly converging into doing atomic outflow, and hopefully we can conclude on how PRIMA can be useful on this end. And so this is showing a spectrum, a typical spectrum like Herschel observation toward a protostar. So show a lot of lines. So you can actually run line survey with Herschel, which is pretty cool. Would highlight a few things here. So one thing is that we see a lot of CO lines. So all of these like red label, like red numbers going from like CO 43 all the way to CO like maybe 44, 42 to 41. Those are all of the CO letters like tracing higher JCO line, and you can trace very high excitation CO with Herschel. And it also cover some O1 like atomic oxygen lines, and that's at 63 and 145 microns. So I'll come back to those lines in a bit. And we also have like C2 and C1, and those are like, a very common atomic and ionized gas tracer here. So they all have they can help us to indicate the gas properties in the atomic and ionized gas ionized phase. So we actually can use Herschel to quantify a lot of outflow structures in protostars. In a few, like this is many years ago, we did a survey with Herschel in about, can't remember, about 20 protostars or so. So this is using a Spire instrument, so primarily targeting a CO. So this COP Spire means CO in protostars. This is showing a demonstration of what we can do here. So we observe like CO lines from like J equals 4 to J equals about 41 that we have robust detection, and then they allow us to probe a wide range of gas properties, right? So by characterizing those gases using rotational diagram, which is shown here, we can actually look into like maybe 2 or 3 or 4 temperature components. That's what we conclude. That's what we end up using. And you can see those temperature components ranging from about 50 Kelvin to about 300 Kelvin that we can get this from this particular example. And we can do this for, about the entire sample that we have, about 20 or so sources. And then if we just take a very empirical approach to compare how this rotational diagram actually change in different type of source. So now I'm comparing the class 0 and class 1 source, which is the earlier stage of source, that's a black, and that's the magenta color here, and compare with, for example, the T-tar star and the Herbig star, that's a more late phase. You can kind of see that, for the protostar, it seems to be following more or less the same shape and location in the rotational diagram here. But for the T-tar and the Herbig, that seems to have a little bit lower in around maybe like 1,000 to 4,000 Kelvin kind of range in energy. So this could indicate that those late stage sources have less highly excited CO gas, and this could be, due to their mass, but it also could be due to the shocks and outflow just more energetic and in the early phase, they have more material to interact with. So therefore, it's easier to excite these high JCO lines in the protostars. So going back to the temperature, like I mentioned, by modeling maybe 3 or 4 temperature components, we start seeing a range of temperature. But one thing, once we put everything together with all of our sources, we start seeing some interesting trend. We start seeing there's this like 300, maybe like 300-ish components, like showing if we plot all of those temperature components in a histogram. We start seeing this like consistent bomb, around 300 Kelvin. There's another components at around like less than 100 Kelvin as well. And compared to another study, more or less at the same time, look into a larger sample, but only for CO with J equals 14 to maybe 25. So I think it's 14 to 45. There should be a typo here, but they probe a lot more higher excitation CO here, and they don't have this low temperature components. But if put everything together, there seems to be a low temperature component at around 100 Kelvin or less, and there's a 300 Kelvin component, and maybe there's a 700 component that's persistently appears in these protostars. In Herschel, this emission is very difficult to resolve. So temperature property and physical properties are typically the one we run with. So there seems to be some commonality that we actually seen across protostars. So that's quite interesting. And then in the WISH program, where they predominantly look into the water, they actually propose a several scenario for shocks and outflow. This kind of like a little bit overwhelming at a glance, but basically there will be a wide angle there's a wide angle outflow, and there's basically a jet coming out interacting with outflow, creating shocks along those like outflow cavity wall. So sometimes we call it cavity shock. So but there's also some people think there could be a disk wing also creating this shock structure. So but basically those means that they're shock material, but not the most highly excited shock, and they seem to distributing in a larger area along a cavity wall or within the cavities. And there's also something called spot shock, which is likely the shock along the jet, and there seems to be have highest velocity and therefore could correspond to the highest temperature components that we see, those like 700 Kelvin components. For the one we see here on the right, the 300-ish Kelvin component is likely tracing either the cavity shocks or maybe the disk wing within the outflow, and the less than 100 Kelvin component is likely tracing by the entrained gas in kind of like the cold and outflow cavities or the outflow cavity walls surrounding the warm inner components. And oh yes, so another thing that we can use, or kind of the thing we hope we can get most of the time to characterize outflow, is actually have velocity resolved information. And that's why ALMA has been really wonderful in characterizing outflow, because it provides very high quality velocity information. With Herschel, we can do it for a few lines, and it's very time consuming. The bandwidth is very limited, but here show one of example of water observation for 3 protostar here, and we see there's a broad component at the center, and there's some narrow component at the center as well, and that's probably tracing the quiescent gas, and the broad component probably traces this cavity shock, and there's this like very high velocity components and at around maybe like -80 or something in some protostars. You can see it in BH71, it's the EHV, that's the extreme high velocity components, and in W3RS5, they also have this like others, which is high velocity component as well. So those are likely tracing a spot shock or tracing the shock in a jet in the outflow that we can clearly identify from kinematic information. So we're seeing a lot of these like intrinsic spectrum in waters, in molecular tracer, but what exactly, where's this atomic outflow? Like, how do we use it? What does spectrum look like for atomic outflow, and how do we associate atomic outflow in this kind of scenario here. So far I've been talking about CO and water. There's still not atomic outflow here. So going to this kind of part of my talk, I want to kind of bring ourselves to the basic a little bit to see how we can what kind of outflow structure, how this velocity structure actually appear in the protostar. So I want to start with a very, very simple model, like spherical outflow model, and try to show you how the different shock component actually occur. This is basically adaptation from the model in Hollenbeck 1985. So assuming this is my protostar in the envelope, and then we have like a high velocity wing, high velocity outflow coming out at around 100 kilometers per second. So it will sweep up the ambient gas, just push away all the ambient gas to the outer radius, and this sweep up motion drive a shock, a low velocity shock, so likely molecular, about 10 kilometers per second into the surrounding envelope. But this kind of sweep up motion also drive a reverse shock with shocking the wind by itself. So this is and because the wind's coming out at 100 kilometers per second, the outer shocks at 10 kilometers per second. So this wind shock, this reverse shock, also on the order of 100 kilometers per second, coming into the wind itself. And this wind could be very likely ionized or atomic when it first launched. So in Hollenbeck 1985, he derived a very simple, with some assumption of course, but with very simple relation that we can relate the O1, the atomic oxygen O1 63 micron line luminosity directly to the mass outflow rate, and therefore mass accretion rate. And that's basically assuming all of your O1 is probing basically your outflow goes through a shock, and your atomic oxygen pick up that shock. So there's a very simple assumption, but it provides at least zeroth order estimates on the accretion rate. And why O1? Because in these kind of shock region, and O1 tend to be the most efficient coolant in those regions. So again, this is showing a modeling result from Hollenbeck and McKee in 1989, and it shows that O1, across different velocity here seems to be the most efficient coolant here. So this is the most obviously tracers that we can use to trace these shock regions. With Herschel, we do see O1 emission quite a bit, pretty consistently. So this is using an instrument called PAX, which is very similar to a FIFO-S emission instrument I'm going to mention later on SOFIA. But it's basically a really nice spectrometer covering a wide range, but have very, very limited velocity resolution. But we do see in this source L1551 RS5, we do see there's some velocity shift, in the O1 line. If I zoom into the center part, you can see the O1 line is kind of offset by maybe 50 kilometers per second, but note that the velocity resolution is about 200. So it gives a hint of an outflow traced by this O1, but it doesn't really give a definitive proof of what's going on with this O1 emission. And to go further on that, we turn to SOFIA. So SOFIA has this instrument called GREAT that provide very nice resolution, like RF, like, I don't know, 30,000 or 50,000 to observe. I think can observe both 63 micron and 145 micron O1 line. So we want to use it to resolve those those velocity structures in the O1 line we see for the SEM source. So again, this is a SEM source, and this is showing the O1 line on the left, C2 on the right. The background is our Herschel observation. So you can see it's a similar structure, kind of elongated along the northeast to southwest for both O1 and C2. That's tracing in general outflow direction. And we place like basically 3 beams along the outflow, hoping to capture some O1 line. We also try to get some C2. C2 provides some constraint on PGRs. So because some PGR can also contribute to O1, so we want to have some check to see how much of O1 is actually coming from PGR, or if there's any. And our observation is a little bit less sensitive than we expect it to be, or more like the instrument itself is not very sensitive to begin with. So we do manage to get some detection actually toward the center, which is the middle row here for O1 and C2. For C2, you can see we see these narrow components at the center, suggesting that's likely tracing the quiescent perhaps outflow, or basically kinematic-wise the material that likely excited, or in this case in a PDR or something. But what's really interesting is this O1 emission toward the center have this like broad wing toward the to the blue shift components, blue shift velocity. So and we think that the missing part of the red is likely due to opacity effect because the inclination of source. But so if we assume that if we take that as granted, if we trust that that's a right interpretation, then we can kind of do some simple component decomposition of this spectrum, and we can get this like central broad components, and also we have this like extremely high velocity and extremely broad components in O1 line here. And if we compare with other tracer here, like CO or water of the same source, this kind of extremely broad component really only seen in this particular tracer in O1. You know, other lines only see the central components as well. So we think if we go back to different scenario I mentioned about disk wing, cavity shocks, or spot shock, really like only the spot shock or the jet can give you this high velocity displayed components, as opposed to other shock component, other wing components, and mostly it's a broad component centered on the source velocity. So we think this O1 lines, this broad wings tracing this high velocity jet that we just don't see it before. So this seems to have an atomic jet in the source that this uniquely traced by O1. With the atomic oxygen observed, we can also actually do some chemistry as well in the shock region. So this is showing the oxygen abundance in different star forming regions, so from diffuse cloud to like comets. And I'm going to focus on the shock part. So this shock part seems to have very little atomic oxygen here, and also there's very few, maybe only a handful of measurements of a atomic like basic oxygen abundance in the shock regions. And with SOFIA, we have only I think 2 detection in the low mass protostar and a few more in high mass, but still total is less than 10. And so another study on the atomic oxygen is in the shock region of NGC 3033 RS4A. That's R1 here, shown on the middle panel here. And again, they're seeing this like high velocity component here at around like 40 kilometers per second. And they conclude that about 50% of the total oxygen is in atomic oxygen. But if we go back to our spectrum, in this jet components, that this high velocity, extremely high velocity component, we only see in O1. I think that's fully atomic. That's 100% atomic oxygen basically. So in that part, we never seen before that is a predominantly atomic form. And in the central part, in the cavity shock, the central part, we ran some calculation and showed that the atomic oxygen only actually take up to about 70% of total kind of volatile oxygen budget. So that's a very different scenario compared to previous another source with only like 15%. So so that's actually quite a different scenario that we're seeing here. And again, we're seeing this kind of some detection in a few other sources as well. This intermediate protostar called Cepheus E. And now we're seeing O1 mostly tracing the same thing as a CO. That's the red spectrum compared to the black spectrum, so suggesting they kind of have an equal part, at least from the zeroth order, so they have like equal contribution to the oxygen budget. In the several high mass sources, we also obtain, people also obtain like high resolution O1 emission. For example, on the right, showing that we actually also seen some high velocity components in this H2 region. On the right, we also see also high resolution, high velocity component for O1, but we're seeing a lot of absorption. This is O1 63 micron line, and that could easily suffer from self-absorption, especially in high mass sources. So to our high mass sources, we're also conducting some survey using so-called FIFO-S instruments on SOFIA. So this is a part of a SOMA survey that we did covering about 18 high mass protostars. So this is a work led by my student, Teddy Oki. In this particular study, in this particular sort, he's discovering O3 detection in high mass source, which is very rarely seen, mostly because we just don't have this coverage in our previous observation, in our previous observatory. So Herschel doesn't go that low. And so PRIMA will be able to do a lot of things for this O3 52 micron line. But in this case, we're seeing O3 and O1, in the source, and we see some interesting velocity displacement for the redshift and blueshift velocity, especially in O1 and O3. We think this is tracing outflow in about, in roughly northeast and southwest direction. The broad line width of these lines consistent with an outflow origin. And then we actually search for this molecular counterpart using ALMA data. So we look into ALMA archive and finding 13CO and then C18O observation seems to also trace similar direction in terms of velocity structure. So we're planning to submit this paper really soon. I think I'm gonna meet with Teddy tomorrow to figure that out. But at least we think we're finding a very interesting case where we detect a rarely detected O3 line and actually trace a ionized part of outflow in the protostars. And so how PRIMA can be useful for these kind of study is that if I take this, I think this observation we did with SOFIA grade is really a nice example showing what do we need and what is really lacking in SOFIA basically. So I plotted the virus high resolution kind of like typical line profile from instrumental resolution here. So the forward Hamax of virus at this wavelength is about 40 kilometers per second, which is sufficient to pick up these high velocity components. And more importantly, that the height of this kind of Gaussian profile plotted here is using the minimum integration for virus. So we can easily do much better sensitivity compared to what we can do with SOFIA here, with acceptable resolution, velocity resolution to pick up these high velocity components. And one thing will be useful is why we pick up these components, because we want to know what is atomic jets happening. Are they driving a lot of outflow momentum? How do they relate it to the underneath accretion disk and accretion process, and how this playing the intermediate role between the ionized part of outflow and also molecular part of outflow. So I submitted a geo volume 2 cases on this one, and we think we can select protostar from low mass in a nearby region and to our high mass protostar in a little bit further region, just to have enough sample. So I think this will be a really nice survey to go from a mass spectrum protostar and to see how this atomic component of outflow actually changing as a function of mass in different environments. And yeah, so if I take what we did before with Herschel as a kind of estimate of line flux of O1 here, the lowest O1 flux in our Herschel survey can be detected with 3 sigma after about 2 hours of a PRIMA time. So that's pretty manageable, and that's the lowest O1 fluxes we can have. So we expect with about 2 hours per source we can get decent O1 observation. For some sources we actually need a little bit more interrogation to get the 145 micron line for O1 to mitigate this optical depth effect that I mentioned before that we see in some high mass source, so that we can have a robust flux measurements. But in a very conservative estimate, it's about, if we want to do about 100 protostars just to have large enough sample, it can be done within 500 hours. So and that's a band 2 and band 4 simultaneous observation. So it not only covered the 2 O1 lines simultaneously, we can also get a C2, which probe the PDR. We can also get the O3 line at 52 micron. And so they enable a lot of auxiliary science like related to the outflow sciences here that we try to do here with O1, and it also covers several water lines and several CO lines. So we can, at one shot, we can have a ionized atomic and molecular component comparison here. So in summary, like I think hopefully I convinced you like outflow structure really nested and can really, you really need to have various different tracer from molecular, atomic, and ionized line to pick up different components and to trace the full structure of outflow. And one of the interests to doing outflow study is to probe the most energetic part, because that represent or tightly correlated to the underneath accretion activities. And ALMA has been really useful to detecting, morphologically the colder part of outflow, the CO outflow structure, and measuring the overall dynamics within outflow. But with infrared and far infrared observation, really using Herschel, SOFIA, and JWST, that's where we can pick up those high velocity, high energetic, high temperature part of gas in the outflow. And with JWST, we're starting to see a lot of substructure within outflow. There's a lot more figures that I don't have time to put in here in this talk, but there's a lot of beautiful picture of outflow that have meticulous small structure that I think is very difficult to explain individually, but that represent the physical condition, the interaction of outflow to the surrounding material. And then SOFIA is kind of, to me, feel like a pilot to what we try to achieve with PRIMA here, that show, O1 and O3 stud line can be really uniquely probing the high velocity shock and outflow. And especially the O1, we can see atomic component, atomic jet, perhaps in some protostar. So I think PRIMA has is very kind of PRIMA like very obvious choice to conduct to what we take this kind of study would build up with Herschel, with SOFIA to a next level. But it's fast mapping, its sensitivity, and its decent spectral resolution that we can actually do a survey, large-scale survey for atomic outflow and capturing other components at the same time. So I'll stop here and take your question. Thank you.
All right, thank you so much, Yao-Lun, for an excellent talk and so much going on in those images, such nuanced physics and so many tracers. So we can open up the floor if anybody has any questions to kick us off. Free to raise your hand, or I think there's few enough of us if you just want to shout out. Maybe while everybody else is cogitating, I'll just ask, so in your discussion of the oxygen abundances, you had a component of oxygen labeled UDO, and I wasn't sure what that was. I was hoping you could walk us through that.
Right, that's unidentified oxygen. So I think when people compare the volatile oxygen, mostly in CO, water, and atomic form, and also the oxygen that potentially in a dust, we're still missing some part of oxygen compared to elemental abundance of oxygen. So that's what people label as UDOs. Basically, we don't really know what those basically missing oxygen in this case.
I see. And so it probably can't be in any of the species that, I mean, you see the atomic oxygen lines, you see some the kind of small range of suspects of molecular carriers. So you feel like you have sufficient observations of gas phase oxygen to think that it must be locked in the dust somehow.
Yeah, in a shock, I think we don't really in this kind of observation we don't really have the whole array of things. Like for example, we don't have a constraint on the dust, but I mean, one can assume the dust is destroyed here, but we're not confident enough to make the assumption for this case in particular. But we sort of like take that as given, like, okay, this is how much in the dust and how much in the unidentified oxygen here, and just work with a volatile oxygen ratio here. But if we have a better multi-tracers for oxygen kind of observation, then we could probably indicate whether there's any missing oxygen, like to in turn constrain this unidentified part. But in this particular shock region, we don't really take that approach.
I see. Thank you. Other questions? I can take chair's prerogative to ask one more. So, I mean, there's, like I said, a lot going on in these images in terms of morphology and line of emission and relative level of excitation. Does any of that change on interesting timescales? Like, is there any motivation to go back to some of these observations 5 years later or something like that?
Right. So I think there is. So I mean, let me see if I can find any. Maybe I use this. So this is not the same source I'm gonna talk about, but with JWST we do see, for example, there's one source, I think B335, and we do see we have on the source on the right, we have like mirror observation and near spec observation separated by about 8 months, and they have some overlap region covering the same CO line at infrared, and we do see the CO not actually move just by 8 month timescale. So when you have sufficient resolution, you do see the propagation of certain things. In terms of unresolved observation, I think you still have prospect to see this outflow variability, because we do know protostars do vary on different time scale as well. And for example, B335 here again, it kind of unexpectedly had the peak in luminosity around 2018 and has soon come down. So this is about 2 to 3 years time scale about this variability. So I think one could do some calculation to figure out how much of this luminosity propagation, if it is coming from accretion, and how much times they're going to result into a change in the outflow structure. But then at least we can see the luminosity change and how they react to other tracers that we are seeing here, and kind of help us to interpret those kind of passively heated or passively excited components, and try to see, kind of have a better understanding how to separating those actively shocked material versus the things being irradiated.
Okay, wow, that actually sounds like there's some exciting prospects there then.
Yeah.
Thank you for taking me through it. Good. Oh, Hanai.
Yeah, I'm not expert in this field, so maybe I'm asking something very naive questions. And sorry, it seems I cannot turn on my camera. And thank you for the great talk. So I see you show the CO excitation diagram, but you also before that you also show the H2 maps. But maybe I just missed it. But I think for H2 also can do the excitation diagram. But if you do this and compare to CO ones, I wonder if they are consistent or what they can tell us.
Right. So we do have the excitation diagram for H2 here. I just didn't show it, but they do trace a very different temperature component though, because this H2 line, what we're finding.
Oh, sorry. Go ahead.
Yeah, this H2 line tracing about I think what we get is temperature around 1000 Kelvin. While the CO, even for the highest CO lines, highest COJ transition that we can get is only, we can only go down to maybe a 700 or 800s. But I think that's mostly because they are different. They have different kind of energy level, because if we use the low vibrational CO lines at the same range of that we can cover with JWST, then we can start probing a few thousand Kelvin gas. So maybe it's just because the energy level of the CO lines we're getting with far infrared, and have some small gaps between the H2 here. But if we have observation in the same range, same regions, I think there's some good comparison we can do to see how this, because they're approaching each other, right? So if we can constrain a low excitation H2 gas here well enough, and they basically should overlap with those CO gas that we're getting in a higher J end, and want to see, like, are they mixed well together? Do they still have layer structure and stuff like that? So there's some interesting prospect that we can do here, and that's why we really need to have a good handle on the low temperatures H2 here, because with JWST, we don't have an S0 lines probe robustly.
Thank you.
All right, any last questions? If not, thank you so much again for an excellent talk. And for folks tuning on after the fact, I'm sure that if you have any questions that you can get in touch, and I'd be happy to answer any questions that you might have. And I hope that everybody will join us for the next PCAST talk, which will be on September the 8th with Klaus Pentapodin. So thank you all, and thank you again, Yao-Lun, for an excellent talk, and see you all next time.